Hi everybody, welcome to another section in differential equations. Section 4.1, Introduction, Mass Spring Oscillator. So what we have is a mass spring system. So a mass of an object, and there is a spring. Let's say an object is at rest, is at this point, but we're going to pull that, and then let it just go back and forth. So that's oscillating, go back and forth. So there's a few things that we need to know about the system. First, the mass or the inertia, the mass spring system. So the mass is m, and this has the spring, and the spring has the stiffness k. And when the object's moving, there may be some friction. There should be some friction between the mass and the surface here. Or even though if it is go up and down, there's still air friction. Right. So when we put all those quantities together, this is what we have. So the mass of the object, the spring constant of the spring, and the damping coefficient due to friction. Of course, that spring constant, that obvious. B is a damping coefficient because of friction. Right. Now, once again, now we try to write the function of y, which is a distance from the equilibrium of the mass system according to a function of time. Right. So let's put all together. Newton's second law of motion, F, the force, is equal to mass times acceleration, which is equal to mass times the second derivative, because acceleration is second derivative. So that is the second law, Newton's second law. We have this. Next, Hooke's law. The force, the restoring force of the spring is equal to negative k times y. Now the reason there is a negative because of this. Equilibrium is this. So think about originally by itself, the spring at rest will be like this. But what we're going to pull that over here. Even though the distance is positive, we're going to pull in that direction, it's positive. But the force is negative because this is called the restoring force. The force, the swing will pull, the force acting on the force of the spring acting on an object will pull it backward. So that's why it's negative. And Hooke's law says that the distance here with the force are proportional, and we have the k constant for that. So that's the second one. Then friction. Friction is proportional to the first derivative, which is the velocity. The faster this one moves, the less friction it generates. So that's what we have. And let an external force, maybe gravity acting on this, or maybe some wind blow in some certain direction. So there may be some external force. Put all together, the force acting on the spring mass system on the right hand side is this, and on the left hand side is the Newton's second law. So put them all together, we have this, and move everything that have the variable y to the left hand side, and we have this equation. Now here's some special case of this. Suppose that there are no friction or no external force. We have y equal to cosine of omega t is a solution of the equation, and omega in that case is called an angular frequency. Of course, here we can also say it could be sine as well. Now compute omega. Right. Now, suppose that in this example we have no friction, meaning that B equal to 0. And external force, there's no external force, so external force equal to 0 as well. So we're going to put 0 and 0 into the equation. When that happens, the solution is said to be this. So we're just going to confirm that when B equal to 0 and external force equal to 0, this is a solution. Right, so just exactly what we have. No friction, no external forces. B equal to 0, external force equal to 0. Put all of that into this equation. We don't have B, we don't have external force, so we have this equation. Now, we need to show that this is a solution, so we will take derivative. And then the second derivative, of course the derivative is a function of t. Derivative of cosine is sine, and negative omega, that is the chain rule. And then derivative one more time, that's what we have. So we have the function then we take derivative. Derivative of cosine is negative sine, and then derivative inside is omega. And then we take the second derivative. Now, put those together. The function go to y, and the second derivative go to the second derivative, and so we have this second derivative, and then this the original function. Multiply it out. Actually, we just factor out the common factor. We have the common factor of cosine omega t, factor it out. We have negative m omega squared plus k equal to 0. Now, this equation has to be true for every values of t. So in that case, inside the bracket has to be equal to 0. In that case, t could be anything. So inside the bracket equal to 0, we have this, and so for omega, we have omega equal to square root of k over m. Of course, it could be negative too, but customarily we just choose positive here. Right. If there are no friction and no external force, this motion is called a simple harmonic motion. Once again, if it is sine of omega t, that is also a solution to the system. Right, so that part is simple enough. Now, verify that exponentially damped sinusoid given by this is a solution to the system with this equation. Right, so of course we're just going to take derivative and put in the equation. So first, what is the equation? So once again, in general, mass times second derivative plus b times first derivative plus k times the function equal to 0, equal to the external force. In this case, external force equal to 0. So I write the equation in general form first. Now I'm going to put in all of this information into the equation. Mass equal to 1, so we have first second derivative plus b will be 6 derivative plus k 25 y equal to 0. Right, so this is the equation. Next, verify that this is a solution. So what we're going to do, because that is a function, we check the derivative and then second derivative and then put into this equation. So let y of t be equal to e to negative 3t. By the way, if you bring out a note, try to write small because this might take a lot of space. Cosine 4t. Right, so that is the function. Now we take derivative. Now derivative of this, we have to use the product rule. So derivative of the first term, let me just write this. So product rule u prime v plus uv prime, right? So u prime derivative of e to the negative 3x is e to the negative 3t times negative 3. Should be derivative of negative 3t, which is negative 3. So that is derivative of the first one, right? E to negative 3t times negative 3. And then the second term, v. And then plus the first term times derivative of the second. Derivative of cosine is negative sine. And then we have to take derivative of 4t, which is 4. Okay, so that is the chain rule. Let me rewrite this one. We have negative 3 e to negative 3t cosine t and negative 4 e to negative 3t sine of 4t. So that is the first derivative. Now we find the second derivative. Now second derivative is more complicated. We have the product rule here and the product rule here. So there will be 4 terms, u, v, and then another product rule, u, v, and let's write a plus in the middle. Yeah, I take the negative into the second term. All right. Now, again, product rule, u prime v plus uv prime. Derivative of this, once again, is going to be negative 3 e to the negative 3t times negative 3. Yeah, so that is, once again, derivative of e to negative 3t times negative 3, and there's a negative 3 in front of that again. So cosine of t. So that is u prime v, and then uv prime. U v prime, derivative of cosine for t. Right. So good thing that I haven't messed up so bad. Just I forgot the 4 there. And the 4 here. But other than that, still okay. So u v prime, derivative of cosine 4t is negative sine 4t times 4. That first. And now derivative of this. I did mention that we have to write very small, right? Right, u prime v so u prime and then v and then u derivative of sine 4t is cosine 4t times 4. Right. Now let's simplify this first. Negative 3 and negative 3, that make it 9 e to negative 3t cosine 4t. Negative 3 and 4, negative 12, e to negative 3t sine of 4t, and let's see negative and negative at plus, negative and negative, that again is a plus, e to negative 3t sine 4t. Actually those two are the same terms, right? And then negative 16 e to negative 3t cosine 4t. Right, so that's what we have. Now we substitute this into the equation. So substitute y first derivative and second derivative into the equation. Right, first, this is the second derivative, so I'm going to write all of that. By the way, I will combine the middle terms. It will be just 24. Right, so we have 9 e to negative 3t cosine 4t plus 12 and 12, that's 24 e to negative 3t sine 4t minus 16 e to negative 3t cosine 4t. So that is the second derivative. And then plus 6 times, derivative is this, and then plus 6 times the derivative. You see I keep the color coded, keep them color coded. That is the derivative, that is second derivative. So we write negative 3 e negative 3t cosine 4t negative 4 e to negative 3t sine of 4t. So that is the derivative. Then we have 25 times the function. Or 5 times e to negative 3t cosine 4t. Equal to 0. Yeah, so just substitute the second derivative, first derivative, and the function into the equation. Right, now of course multiply them out and combine like terms. Now as you see in this case, I try to keep things organized. We have the derivative, second derivative, and then the function. Now combine like terms. So if you notice that there's a trick to combine like terms as well. So when we look at all of this, what we see is that we have either e to negative 3 cosine t or e to negative sine t, right? So the cosine, I'm going to draw 1 underline. The sine will be 2 and cosine is 1. Now if we factor all of those terms out, so the first thing we will have e to negative 3t. Right. So if we factor it out, how many of them left? If you factor this out, there will be 9 of them left, right? That's the first one. we should combine those terms as well, right? That's fine, just write negative 16 here. Right, so that's what we have. Next, there's 6, and then negative 3, that has a cosine, so we have 6 and times negative 3, and then e to negative 3t cosine 4t. Sorry, forgot e negative 3t cosine 4t. Yeah, so factor that term out, we should have this, and then we have 25 of them. Right, so that's what we have for the e to negative 3t cosine 4t. Now how about the other terms? E to negative 3t sine 4t. We have 24 and then this term have that as well, 6 times negative 4. Yeah. So get used to do things like this, because later on this will save you a lot of trouble. Multiply them out, combine like terms, it's the same thing. But just recognize how many different terms we have and factor it out, and then just combine the numbers. So what we see here, of course, 24 minus 24, that's 0. So 0 times something, anything, still 0. Now we have here is 9 and 25, and then 16 and 18. So 9 and 25, that's 34, minus 16, and then minus 18. Of course, that is equal to 0 as well. So we have 0 times that and 0 times that. And we have 0 equal to 0, which is confirmed. Right. Later on, we'll do a lot of problems like this where we take derivative and then put it back into the equation. And combine like terms, I recommend that you do like this. Rather than, of course, you can multiply them out and combine like terms. But yeah, just recognize how many terms we have, and then just write out the coefficient. If there's something in front of it, multiply 2, make sure we have that too, like 6 and negative 3, or 6 and negative 4 in here. Yeah, should be mindful of that. But like I said, we do plenty of problems like this. So the bookkeeping, the more organized you are, the better when we do this kind of problem. Right, let's look at another example. I suppose that an external force is F equal to sine of omega t. So this is omega, and this is also omega. So this is the lowercase omega, this is the capital omega. Suppose the solution is A equal to cosine cosine of omega t, B plus sine omega t. So suppose that is the solution. So we have that. So we have the function, we take derivative, and we take the second derivative. That's what we have. Substitute into the equation and then combine like terms. Let's see if we can combine like terms here. So what terms do we have? Notice that in this case, omega, the variable is t. Remember, when the term that we factor out has to be a variable, everything else are constant. So let's look at what we have here. We have cosine and cosine and cosine, and then we have sine Now just combine like terms. Right, if we factor out sine first, we have negative b omega squared, right? And then negative a omega, and then 25 times b. That's good there. Next, for cosine omega t, we can factor out negative omega square a and b omega and then 25a. Now, what next is kind of like calculus 2 or pre-calculus undetermined coefficient. If we have that term equal to that term on the other side, the coefficient have to be the same. Meaning that if we only have one sine of omega t on this side, then the coefficient 1 has to be equal to all of that. So this coefficient has to be equal to that coefficient. So that's why we have this coefficient is equal to 1. Next, we have that, but on the right hand side we have no term of cosine omega t. There's no cosine omega t, so we make that equal to 0, and cosine here and cosine there, the coefficient has to be equal, so that coefficient is going to be equal to 0. So with this system of equation for a and b, it can be shown that this is the case. So yeah, the way the technique that we do this kind of problem is just take derivative, put it in the function, combine like terms. Okay, the more organized we are, the better we are at this problem. Right, but so that's a little application, and what we see here is an application of a second order differential equation, and this differential equation have the special all of them, all the coefficient are constant. So what we're dealing with, what type of problem we're dealing with now is second order, I mean we could say linear as well, so linear second order differential equation with constant coefficient. So once again, linear because there's no power for y second prime or y prime or y, so that's linear second order differential equation with constant coefficient. So this is the type of the problem with that we're dealing with. Right, and that's we spend the whole chapter studying about those and a little more. Right, but I'm going to stop the section 4.1 here. As always, thank you for watching. See you in another video in differential equation.